Very good morning, one and all. Today we are learning the subject of circuit theory or network analysis. We will go through the chapter of the steady state and transient response. In this chapter, we will study today the Laplace transformation and the numerical related to the Laplace transformation. In the previous lectures also, we have studied about the Laplace transformation of a basic concept related to that, how the circuit will affect, how the RLC will be affect while you are going to calculate the responses with respect to the time period. And by applying the transformation from the time domain to the frequency domain or vice versa, what will be the effect of that particular circuitry? The circuit may be the series circuit, the circuit may be the parallel circuit. So what will be the effect of that Laplace transformation on that particular series and the parallel? If we are going to keep the switches there and that switch is going to be open and the close at the time, what will be the effect on that particular circuit that we are going to observe in this case? That is nothing but the transformation by using the Laplace. So here we are doing the transformation of the circuitry of the RLC by connecting the pure R, by connecting the pure L, and by connecting the pure C. With the sources, we are observing all the responses. Okay, in later on we can combine the combination of the RL, the combination of the RC, and then RLC, and you can apply the Laplace transformation. Okay, even though we are doing the Laplace transformation, definitely we should know the basic concept which are related to simplify, reduce that circuitry. Just like you are the what you can say, if closed circuitry is there, you need to apply the KVL V minus IR is equals to 0, and whenever the circuitry is closed, you can apply the Ohm's law also. So in this way, you should take care even the transformation from the time period to the time domain to the frequency domain, and the frequency domain to the time domain. Just like the T will be changes in terms of the S, and the S will be changes in inversely what we can say response of the T in terms of the T. So all the conditions you should remember while you are going to simplify the numericals which are related to Laplace transformation. If we are having already, we have studied in the transformation circuitry, if pure R is there, how we can convert that time period into the frequency domain, or you can say in the Laplace, the relationship between the, what we can say, the voltage and the current, you can observe easily. If you are having the pure R, if you are having the pure L, if you are having the pure C, and the voltage is across that particular component and the current is flowing through that, so how they are changing, that already we have observed in the last session. And we need to write the equation with respect to the time period, what we can say the voltage equation, we need to write the current equation, and we need to simplify that entire equation for calculating the known parameters. So see here how I can write my voltage equation in what we can say in the time domain, and if you are doing for the frequency domain by converting the transformed in the Laplace, so how we can convert that, you can observe easily. So if you are writing for the L, so what is the effect of your V of t with the whenever the current is flowing, that is L into di by dt. If you're writing for the voltages, what will be the effect? So okay, so that you can observe easily. So that all these things we should keep on in our mind. What will be the effect of the voltage and the current if the pure R is there, if the pure L is there, and if the pure C is there. Okay, if we are talking about the inductor, definitely we should think about the current which is flowing through the inductors, that is nothing but L into di by dt. As per the Ohm's law also, you can write that equation, and later on you can apply the KVL, and you can simplify that equations. The equations may be the 1 and 2 with respect to the voltage source and the current source. Okay, and you can apply that one. If you are having the capacitor, pure capacitor, so how the voltage across that capacitor, that is nothing but C into dV by dt. Okay, so these are the storing element L and C, and we need to observe the voltage equation and the current equation in the time domain. Similarly, just convert of the transform into the frequency domain with respect to the S, that is T will be converted into the S, and see here the integral part and the derivative part can be converted. Okay, as per the transformation. If you are having the C, what will be the effect of your C? Okay, how that C will be changes into 1 by CS, and later on if you are applying across the voltage, so what will be the effect of that? If I am writing for the current equation, what will be the circuitry? And if I am writing for the voltage, see here the difference in the circuitry. So these basic things you should know. Okay, if there is a, what we can say, the combination of the circuitry, that is nothing but you are combining the resistor and the inductor, both are in series, and the voltage source across that, and the current is flowing through. And if we are interested to convert that time domain into the frequency domain using the Laplace, so how it is possible, that we will observe today. And even the resistor which is in series with the capacitor, so what will be the effect, the same here. How we can write the, and how we can show the relationship between the V and the I, that also we can observe. And if you are having the combination of your the R, L and C, what will be the effect of that? So this is too important, how we can transform in the Laplace. See here the observation, if the resistor and inductor are connected in series and the switch is applied to that R and the L. So individually we need to observe the conditions, so the changes. Okay, so if pure R is there, already we have seen the condition, the changes. Okay, what will be the effect of the R, pure R? Similarly, what is the effect of your the L? And then later on you can combine all these things, the R and the L. Okay, if the switch is open, what will be the effect? If the switch is closed, what will happen? Okay, and how you can convert the time domain into the frequency domain. So this is the basic circuitry, simple circuitry, that is in the series circuitry, you can say, that is R is connected in series with your L, and the circuitry at present is open, switch is there, and the current is whenever the switch will close, definitely the amount of current will flow through the entire circuitry of your the RL, and the voltage is across that the component of your the RL and the L. So whenever the switch is going to close, after closing that switch, when the T will be greater than the 0, at this particular instant T is less than the 0. Okay, that is nothing but the 0 minus, you can say. And when the switch will be closed, at that particular instant T will be exactly 0, and later on once the current will be start to flow, T will be greater than 0. Okay, previously T is less than 0, and later on after closing that switch, T will be greater than 0. So see here, after closing that switch, so definitely that time period will be converted into the what we can say, the frequency domain, that is nothing but I of S. T will be converted into the S. R and the L is there. There is no effect of the R. Okay, but definitely that effect will be just because the basic fundamental is here, that is nothing but the R is in phase. Okay, R is in phase. So see here the inductor, whenever the inductor is there, that will be your the LS. Okay, and the voltage across that is nothing but V by Fs. So for that, after closing that switch, T will be greater than 0. The transformation will be happening. You need to apply the KVL to the entire mesh. We are by the same mesh, so close path. So just apply V minus IR is equals to 0. Okay, so or you can say V is equals to IR. Later on, next step will be V is equals to IR. So what is that? V is nothing but the V by S. What is the R? Here the you can't take only the register. You should think about the R as well as the L. Okay, just because of the combination, but just because of they are connected in series. That's right. Okay, so for the R, V is equals to IR. So I, that is nothing but I of S. What is the R? R will be along with that. What is the L? L into, again the LS is there. So see here the LS dot of I of S. So take this I of S as a common in both the inductor and the resistor, and these two combination will go in the denominator. So V by S, V, and that S will be here. So in this way you need to adjust also to get in the proper way, because if you are not getting in the proper way, you will not be able to do the partial fraction expansion and other parameters. So already it might be you have studied in the mathematics. Okay, this the Laplace transformation, the partial fractions, the basic fundamental must be clear while you are going to simplify such kind of equations. So see here how that we this L will go up. Okay, how you can multiply twice the numerator and denominator of this R by L to get in the proper form. So in this way, see this if the meaning should not be changed, whether you are going to multiply or divide by anything, the meaning should not be changed. Okay, so S will be as it is, this V by S, this is just for the adjustment, that is nothing but the L, and this S plus R by L. Okay, so later on what you need to do after getting in this in that standard form, you need to apply that partial fraction. Okay, expansion of that I of V S will be as it is. So this is one part, S is individual one part, and this bracket is the other part. So A by of S plus B is uh, S plus R by L. So see here the segregation, see here the partition of here the A and the B in the partial fraction. So S is the one and the S plus R by L is the other one. And later on what will happen, this A you need to keep one side, and this S will be multiplied with the I of S, and after S nothing is there, so definitely S will be equals to 0. So in this way, S into what is that I of S? I of S is nothing but this entire bracket, that is V by L. S into bracket S plus R by L is nothing but your completely I of S. So at the place of I of S, just completely keep this one, and later on you just apply wherever the S is there, that S is equals to 0. If you are going to apply this S is 0 0 0, so likewise how many term will left? LL will be cancelled out, these three S will be 0 and LL will cancel out. Only the remaining part will be your the V by R. Okay, after substituting the S is equals to 0. Similarly, the B is equals to, what is that? B is nothing but the next bracket, that is nothing but S plus R by L, and that will be multiplied with your the I of S, just like your the A part. Okay, so B, if you are keeping with the B at one side, definitely this S plus R by L will be multiplied with I of S. And what is my I of S? This entire complete thing is nothing but my IFS. And later on, S is equals to, what will be the case at the place of S? S will be equals to minus R by L. So you need to substitute the value of your the S, that is nothing but minus R by L. Okay, so wherever the S is there, you need to substitute that part, and see so how many things is going to be cancel out. Okay, you need to observe which things are going to cancel out, whether the LL will cancel, whether the RR is cancel, and whether the other part. So likewise finally you will get S for the B part, that is nothing but B minus V by R. Later on you just substitute the value whatever you got the A, whatever you got in the B. So A is nothing but V by R, and B is nothing but minus V by R again. So after going to substitute here, what is where you need to substitute this equation? From where you have started, that is nothing but the partial fraction of expansion. So IFS, so substitute the value of A here, substitute the value of B here. Okay, that is nothing but V by R minus V by R. Likewise, okay, so later on again after substituting this in the IFS, just take the inverse Laplace transformation. Inverse Laplace transformation of this IFS. Okay, again what we have done at the beginning, what you need to keep remembered, the procedure, the circuitry will be there, convert that circuitry. Okay, the do the close path, what we can say, the close the switch, then observe the circuitry, convert that time domain into the frequency domain, apply the KVL. Okay, write the equation, do the partial fraction, and after getting the final IFS, you just convert, take the inverse Laplace transformation. So this I of t will be converted into the IFS will be converted into the I of t, and this part, that is nothing but your the V by R and the minus V by R. This will be converted V by R minus V by R e raised to the power, that is a what we can say, the complex equation, e raised to the power minus R by L of minus R by L of that T is there. Okay, so again this V by R will be as it is, and you can take the common V by R. So V by R will be common in bracket 1 minus a raised to the power minus of in bracket R by L of T. So okay, so in this way this will be your the final equation, you can say. Okay. The next is nothing but if you are having the R is connected in series with your the capacitor. Previously we have seen that the R is connected with the inductor. Okay, now you just observe the second case. That is nothing but if the resistor is connected with the capacitor, what will be the effect? What should you should remember? First thing, close the switch. Okay, and observe the time domain into the frequency domain. What is the effect of your after closing the switch? What will be the effect of the time domain into the frequency domain? Effect on the R, effect on the C, effect on the sources. That is nothing but either the voltage and the current source, both. So not either on the both, that is nothing but voltage source as well as the current source, the resistor along with your the capacitor. So you will be able to observe, then later on apply the KVL. So whenever you are going to close the switch, definitely the time period will be greater than the 0, and you are going to transform that network or the circuitry. Okay, and you are going to apply the KVL to the mesh. So what will happen for the V? Already we have seen in the previous case, that is V will be V by S. The capacitor will be your the 1 by C of S. R will be as it is, and the current will be I of S. Now just apply the KVL. V minus IR is equals to 0. Next step will be V is equals to IR. So here along with your the R capacitor is there. So the V will be V by S is equals to IR is nothing but I of S into R. What will be the C? That is 1 by C of S into I of S. Now in these two cases, I of S is the common and V by R, just for the sake of what is the simplicity, these are the adjustment, but be remember the meaning should not be changed whenever you are going to apply these two numerical numerator and the denominator in a such a form. So the meaning should not be changed after cancelling and other things. So here V by R, that is come into the denominator of this numerator upper portion, and as plus 1 by RC. 1 by RC, just because they both are connected in series. Okay, so see here, this is one combination, this is the other. By taking the inverse Laplace directly, because in this case there is no as such equation for the equation. So this I of is directly we are having very small, what we can say, there is a single, so no need to do the partial fraction, only S plus 1 by RC, because S is equals to again the 1 by RC will be there. So there is no need to do the partial fraction, directly you can take the inverse Laplace of inverse Laplace transformation. So I of S will be converted into the I of T, and this V by R, that is numerator, will come at one side, and exponential, the denominator whatever you will have, the e raised to the power 1 by RC e raised to the power, that will be S is equals to minus of that, because at present is a plus, S is equals to minus of 1 by RC, minus of 1 by RC. So similarly, so V by R will be at one side, exponential of e raised to power minus 1 by RC will be converted into the time domain. So that is nothing but the T. So when the T will be greater than the 0. Now the last part is nothing but when the resistor, inductor and the capacitor, all these three together are connected in series, and the switch is there, and that switch is at present open circuitry. Okay, so what we need to do, we need to observe always the circuitry, whether that circuitry is open and the close. If circuitry is open, what you need to keep remembered, that is at present that is in the time domain, and we are interested to convert that time domain into the frequency domain after closing that switch. Once you close the switch, you can observe the T will be greater than the 0, and you are going to transform the network, okay, whatever you are having. So what will happen? Consider the series RLC circuit network is shown here. When the switch at present, when the switch is closed, the switch at that particular instant T will be equals to 0. Once the current start to flow, T will be greater than 0, and you are not going to do the transform the network. How after doing the transform the network, what will be the effect of the circuitry? What will be the effect of circuitry? So definitely no need to again redraw the switch. Once the switch is closed, definitely the amount of a current will be flow through the R, through the L, through the C. Okay, likewise, and the voltage across on each the component. So see here, so V is nothing but again the V by S will be here. Okay, and you are the, what you can say, I is nothing but the I of S, R will be as it is L of S, and 1 by C of S. Likewise you can apply the KVL. So see here the three combination, already we have seen the R, L, N in the first case. The second time we have seen the R and the C in the second case. Now R, L and the C. So R I of S, LS into I of S plus 1 by C of 1 by C of S into I of S V by S. So now the here the I of S will be completely common in this, and then the V by L, this will be multiplied in the both, that is nothing but the numerator and the denominator by the L. After multiplying that, so V by L S square plus R by L of S plus 1 by LC. So see here the in the standard form, the equation must be in the standard form while you are going to write the I of S. We remember that should be from the Laplace transformation equation, so that we can do easily, we can simplify it easily, we can reduce the circuitry easily, just sake of that only. So V by L S square plus R by L of S plus 1 by C of S. By taking the V by L, so what will happen? C is common, so you can segregate two equations here, because just because the quadratic S square S and the constant term, so you need to take the S1 and S2. So S minus of S1 and in other bracket S minus of S2. So what is that S1 and S2? You can observe whenever you are having the quadratic equations such that, and these two are nothing but the roots equations, already you have done in the maths. So S square plus R by L of S plus 1 by C is equals to 0. While you are going to simplify this equation, such type of equation for it to that time. So what will happen for the S1, that you need to multiply, you need to take out the root of all, okay, you need to simplify. So that is possible. You can segregate two switches, that is S1 and not switches, but that equation to write to simplify that quadratic equations, S square plus R by L of S plus 1 by LC. So you need to do the segregations. Finally, you can get in terms of the, you can say the alpha and the beta form, that is S1 and the S2, and you can substitute these terms. Okay, so what is finally the alpha? Alpha will be equals to R by 2 of L. What is the beta? Beta is nothing root of alpha square into the omega 0 square. What is what the omega? That is nothing but the angular frequency. Okay, at a restaurant you can say at present. Okay, so at the initial you can say, so that is nothing but 1 by root of LC. Just because of this R, L and C, these are the changes. So always keep remember, whenever you are having R, whenever you are having L and C, all these three together, that time in a such a way only you need to simplify that numerical. So alpha you got, beta you got, the omega is 1 by root of FC you got. In a many of the test book might be they written here the F0, that is nothing but 1 by root of LC like also. Otherwise 2 pi f already angular frequency is there. Okay, so here after doing the partial fraction of expansion I of s, so a by s minus of s1, b by s minus of s2. So if you are taking this a at the one side, so I of s will be multiplied with s minus of s1, and later on s will be equals to s1, because this is 1, this is 2 will be equals to 0 anyhow. S minus s1 is equals to 0, s minus s2 is equals to 0. So here what will happen, the s is equals to s1, and here will be s is equals to s2. So v by l, same like previous one, s minus s2. If these two, if we are going to substitute the value, finally you will get as the a is equals to v by l s minus of s2. If you are going to simplify, b is equals to I of s into s minus of s2. So you will get a minus v by l of s1 minus of s2. If you are going to substitute this value in the I of s equation, the at the place of a, at the place of b, if you are going to substitute in the I of s, you will get as v by l s minus of s2, 1 by s minus of s1 minus 1 by s minus. This you have taken as a common. V by L you have taken as a common. After taking this V by L common, S minus of S1 in bracket, if you are going to simplify, you will get the same equation like you the previous or the above equation. There will not be any changes, meaning will not be changes, only the adjustment will be there. Okay, so after getting the final IFS, you need to take the inverse Laplace transformation. So again, this frequency domain will be converted into the time domain, and this V by L will be there, this one, and you need to do for the inverse Laplace, that is e raised to the power exponential or complex form, e raised to the power s1, because s will be equals to s1, s will be equals to s1 again, so e raised to the power s1 of t minus e raised to the power s2 of t, you will get like that transformation. Again, these are the two sections. So entirely this bracket you can take as a for the v by l into s minus s2. So you can keep here the gain or the any common form, so that you can substitute to determine the s1 and the s2, because still s1 and s2 are the unknown parameters. So finally for entire this bracket v by l into s1 minus s2, you can take as a a1 e raised to the power so and so plus a2 e raised to the power so and so. In this way, wherever a1 and a2 are the constant term, that we can determine, and s1 and s2 are nothing but the roots of the equation. So in this way, depending upon the values of s1 and s2, you can get the responses. Okay, you can get the responses. So now just we will try to simplify the numerical. If there are values, how we can simplify that numerical with the help of the Laplace transformation. If you are having the circuitry for the network shown below, determine the current of I of t when the switch is closed at the t is equals to 0. So see here, at present the switch is open, and at the voltage phi r t minus of 1 is there at the place of voltage source, and the resistor is a 5 ohm, inductor is a 1 Henry, the capacitor value is 1 by 6 of farad. and the I of t is flowing. So whenever the switch is closed, see here, this e raised exponential form, this time domain will be converted into the frequency domain, and this will be where the phi e raised to the power, because anyhow this time domain will be converted into the frequency domain, that will be where the s t will be converted into the s. So that's why this again this r will be taken as what we can say, taken as in the denominator also. Okay, so if this 5 e raised to the minus s square, 5 will be as it is. This 1 is there, nothing is written, so ls is nothing but l is the 1, s will be as it is. So nothing is nothing but nothing is 1 of s. So here will be the again by, so 1 by cs, substitute the value of 1 by 6. So 6 will be going into the numerator. So 6 by s will be there, and transform the network, apply the cable to the mesh, and for the k is greater than the 0. So voltage source V minus IR is equals to 0. Here V minus IR is equals to 0. So V minus IR, IR minus I of L minus I of C, because we are writing the equation for the R, L and the C. So here this equation 5 e raised to the power minus s of s square minus 5 for the register I of s minus s into I of s, IFS, and minus 6 of IFS is equals to 0. Just try to write into the frequency domain. Okay, try to write in the frequency domain, so you will get as a IFS of you have taken the IFS common, so 5 e raised to a minus s divided by, you just take, always try to take in the standard equation. So what we have done, 5 into a raised to the power s divided by s in bracket s square plus 5 of x plus 6. So again the quadratic equations, see here the equations form the order, the squaring, then the single, then the constant term. So this thing you need to simplify. You should remember how we can get, how we can simplify, how we can do the partial fraction for the sake of partial fraction, how we can keep in the standard form. So that we have tried here in the IFS. This is two important equation while you are going to write the IFS. Totally depend upon the IFS, you can simplify the entire circuitry. So see here 5 e raised to power minus s will be the numerator will be as it is. After segregating this s square plus 5 of s plus 6, you will get s plus 3 and the s plus 2. So see here how many things are here. One is s, second is s plus 3, and third is nothing but the s plus 2. So for after doing the partial fraction, you will get a, b and c. A will be your s, b will be s plus 3, and the c will be s plus 2. So in this way, you can simplify here the three cases: 1 by s, s plus 3, s plus 2, to a by s, b by c by, and if you're taking the a at one side, so what will happen? This entire bracket will be what we can say, s will not be there, because anyhow s will be cancelled out. So if you're writing for the a will be equals to this bracket, and that time s will be equals to 0. Second time s is equals to minus 3. Third time s is equals to minus 2. See here a, b and c. So s is equals to 0 first time, s is equals to minus 3, s is equals to minus 2. And whenever you are writing for a particular thing, that should not be reflected here in the partial fraction. So these two cases will be the first, and the s into s plus 2 will be the second, and last is s into s plus 3 will be in the last. Substitute the value 1 by 6, 1 by 3, and minus 1 by 2 is just substitute in the a, b and the c cases. You will get finally the common term 1 by a, b and the c, and the common is nothing but 5 into e raised to power minus of s. So you will get finally IFS is 5 by 6 e raised to power so and so by s plus so and so. Later on at the end, take the inverse Laplace transformation of this IFS will become as I of t 5 by 6. This will be converting to the unit step function. Already we have seen the tabular form, how you can convert e raised to power minus of s divided by so and so. All these things you should remember, whether it is a ramp function, whether it's a so what we can say step function, whether it's a shifted function or sinusoidal function, whether it's a linear function, that you should remember. So u of t minus 1, then e raised to 1 minus 3 is nothing but again the t minus 1, and u of t minus 1 likewise you can substitute for entire bracket, you can write for that. Okay, so these things you should remember, how we can write the equation. Okay, how we can write the equation. So previously this was the series. Now come towards the parallel form. Here the two switches are there, switch A and the switch B. Two cases will be there. So initially the steady state with the switch is at the position of the A, and at the t is equals to 0, the switch will be goes from the A to B, and find the expression for the V of t for the t is greater than 0. So in this case we are interested to write the equation for the V of t. Previously in the series circuitry, remember we were interested in the writing the equation of your the current, whereas parallel circuitry we are interested to write the equation of your the voltage circuitry. Okay, so see here the two switches are there, one will be at A, one will be at B. When the at A, the t will be equals to 0. Whenever the switch is at B, the t will be greater than the 0 that you need to apply. So if there is a two cases, what will be the effect of circuitry? Observe here. So only two inductor will be that you can say the short circuit, that you need to apply the conditions of short circuit and open circuit. See here, the 2 volt, the 2 and the 2. Okay, so this will be short, nothing will happen. So 2 volt and the 2 ohm will be there. So at t is equal to 0 minus, because t is 0 is nothing but the t is equal to 0 minus, the network has to contain the steady state conditions, hence the inductor will be act as a short circuited. So I is 0 minus, I is equals to V by R. V is 2, R is again the 2, 2, 2 will is nothing but the 1 ampere at 0 minus. Before closing the switch, you can say at a particular instant the current will be 1 ampere. So later on what will happen after getting that 1 ampere, since the current through the inductor cannot be changed instantly. Okay, so it will take a time. So later on the I0 plus will be the same at that particular moment. Later on again the time will be increased, so definitely the current will change when the t will be greater than the 0. Okay, when the t will be greater than the 0. So after applying here for the parallel circuitry, apply the KCL. We remember series circuitry, find out the current, voltage, parallel circuitry, find out the voltage. For the series circuitry, apply the KVL. For the parallel circuitry, apply the KCL, just because of the nodes and all. So at a particular node for t is greater than 0, you are writing for the three cases, the one for the inductor, resistor and the capacitor. So you should remember V of s of 2 divided by 2s. So all these things, for we are applying one for the inductor, we are applying for the resistor, inductor and the capacitor of that. We are writing the equation. So here at a particular node, what will be the effect? See here the V of s of 2. How that is nothing but the capacitor V by R case, V by L case, V by C case. All this you can write in the equation of your the KCL. Take the common V of s, just like you were in the previous series circuitry. I of s we have taken the common. So here V of s will be common, and you can find in a such a way that will be equals to minus 1 by s. So V of s finally 2 by 2s plus 3. So meaning should not be changed every time, I'm telling you. So this 2 you can take a common, and this will be cancelled out. 1 by s plus 1.5 you will get the finally the V of s. Okay, so by taking the inverse Laplace, this V of s will be converted into the V of t minus of s plus 1.5. So here you can take s will be equals to minus 1.5 of t. So V of t is equals to minus e raised to the power minus 1.5 of t whenever you are having the t is greater than 0. Okay, t is greater than 0. Again, this is the series circuitry. So in this case, RLC, 2 ohm, 1 Henry and the 1 farad, V of t is there. Series circuitry, we are interested in into the IFS. We are transforming, closing the circuitry, 2 will be as it is. L of S, L is a 1, so S will be as it is, 1 by of S, V of t applied. So here, what they are asking about that, determine the response of VC of t. That is nothing but, especially the voltage across the capacitor. We are interested in this for the step input. Okay, we remember we are interested especially the voltage across the capacitor. So V of C. Okay, voltage across V of S is nothing but the voltage across the capacitor. V is equals to this particular we have directly by the voltage division rule. Okay, why we are voltage division? We already studied in the unit number 1. Particular thing, the particular current which is flowing through the branch circuitry, particular voltage across that the component. So for such a cases, we need to take the either the voltage division rule or the current division rule. So here the particular voltage we are interested to find out, that is voltage across the capacitor. So VC of S is nothing but V of S. So 1 by of S, 2 plus S plus 1 by S, just because of the R, L and C here in the denominator. Here is the only because of the C. So in this way V of s you can get as V of s divided by square plus 2s plus 1 V of s, then you just do secret s plus 1 squaring bracket is nothing but s square plus 2s plus 1. So you can do for the impulse input, that is V of s you are writing, so is equals to 1 if you are taking considering the V of s as a impulse input. Okay, so by taking the inverse Laplace, V of particular voltage across the capacitor will be equals to, that is for the impulse response, t into e raised to power minus t u of t. So if you're writing for the step input, so V of s will be 1 by s, and the voltage drop across that capacitor by considering the step input, so 1 by s into s plus s square. So this is for the especially for the capacitor, and previously whatever s plus 1 of square. So see here the three cases, this is twice s plus 1 of whole square. So 1 by a by s is 1, s plus 1 will be 1, and then the second time. So in this way a, b, and the c, 3 times you need to take the partial fraction of that. You need to find out the coefficient, that is s raised to 0, s raised to 1, and s raised to 2. Likewise you can find the a, b, and the c, the value of the a, the value of the b, and the value of the c. So a you will get as a 1, b you will get as a minus 1, and the c you will get as again the minus 1. If you are going to substitute at the voltage drop across the capacitor the value of a, b, and the c, you will get 1 by f s minus 1 by s plus 1 and 1 by s plus 1 of whole square by taking the inverse Laplace of that. So by concentrating the step input or as well as the impulse u of t e raised to power minus of t u of t, likewise you can get. So you should remember for the ramp, for the unit step, for the impulse responses, how we can write that expression, how we can get in the standard form. So in this way we have tried to simplify the numerical, so on the basis of your the what we can say uh, the pure R, pure L, and the pure C, and even by combination of your the RL, combination of your the RC, and the